Good evening, everyone. Welcome to CERT-In session on Zero to Hero on assembly language, the language of Cyber Defender, day 4. I once again congratulate you for completing day 1 to 3. And today, in day 4, we'll be going through some very crucial building blocks and concepts of mastering assembly language and paving your path to a true hacker and security researcher. I'd like to point out to everyone to please, during the class, ask questions, as the class is always live. And if there are any interesting or relevant questions, I will be more than happy to answer them in the live chat. If you're asking questions after our session, feel free, as I'll be answering those questions after the video airs. So you'll still have access to all the information that you wish to attain from us. With that, let us begin. Today's topics are called Our Object All Sublime, creating programs that work for us. So the size of the source file, right? The source code file has absolutely nothing to do with the size of the executable file assembled from it. Now, this is something, that people have trouble understanding. The more comments you put in a file, the better you'll remember how things work inside the program the next time you pick it up, right? So this is taught in a lot of programming classes as well, that you should probably write a lot of comments in your code. And I agree with this statement, especially with the source code. As if you're protected the source code properly on your local system, you should definitely go ahead and write quite a lot of comments. And always remember that all of these comments that you write in code are actually stripped away. So when you get your binary file or your executable file, right, for your platform, then you realize that, okay, the size of my code that I wrote and the file that was generated has very little to do with each other. I won't go as far as to say that it has absolutely nothing to do with each other. There's an entire subject dedicated to this. And it is something that a lot of research has been done on, but it's still something that you don't need to think about as a novice programmer. Comments are neither time nor space wasted. Yeah, this is very important. People talk about complexity, time complexity, space complexity, using them properly. I believe comments are beyond these menial topics. You should probably have comments no matter, even if it takes you 7-8 hours to design a simple a plus b equals c calculator. Because the thing is, the code you are writing, right, it becomes extremely descriptive, and not just for you, for everyone else around the world. So say that today you feel like maybe going through a certain section of your code, years later or months later, you will have trouble going back and understanding, okay, what did I write, why did I write that? IBM, back in the day, when they were leaders in the industry, they recommended that one line of comment per line of code is considered good and minimum in any assembly language. So no matter what architecture you're using, highly recommended. Okay. At the top of every program should be a sort of standardized comment block containing some information: the name of the source code file, the name of the executable file, the date you created the file, the date you last modified the file, the name of the person who wrote it, the name and version of the assembler used to create it, an overview description of what the program or library does. So that was commenting in your assembly language programs. Now let's talk about sections, because I've been delaying this for quite some time. So let's jump back in and let's try to tackle this concept of sections, what sections are, how they work, right? Good evening, everyone. So as you can see, sections are multiple. We'll talk about the dot data section first. So the dot data section is one of the three major sections that you will see, okay, when you're dealing with executables. The data section is always going to come first out of the three, followed by the BSS section, and then you have the dot text section. If there's any questions regarding what I just said, or maybe you need more detailed, explanation to what's on your PPT right now, please just intimate me in the live chat. I'll go slightly deeper into dot data because I don't really want to get too much into the analytics side. So feel free to write in the chat. I'll wait about a minute and then we'll go ahead. Okay, so there seems to be no doubt. Okay, so I'll quickly just go through the very basics and move on. So the dot data section contains data definitions of initialized items. Data items. Okay, initialized data is data that has value before the program begins running. This is important. There is a clear distinction between initialized and uninitialized data. All you want to know right now is that before the program starts, so pre-runtime environment, when you define the value of a data item, you initialize it, quote unquote. It's called initialized data. Okay. These values are part of the executable file. So these are usually stored inside the executable files. Okay. Now here's a question for all of you, for all the ones who who want to jump ahead and become hackers. Here's a question. Tell me what happens if an initialized data value is a string saved inside your binary, which is also the password of your binary software. Any guess? What ends up happening in such a situation? I can actually extract those strings out of your binary. And this is a very simple trick actually, done by a lot of hackers and CTFs, tournament, and even real world binaries. If you break them down enough, you'll realize that many times a binary which has some kind of password or license check has the license value hard coded inside the binary file, inside the dot data section, and that makes it so easy to just extract the data and go like, okay, here you go, I got the password, now the binary is going to work and I don't need to pay for the software. And this is something back in the 90s and early 2000s, it used to happen a lot. I don't know how many of you remember one of the classic softwares that we used to use, which was, I think, cam recorder, I think it was called, which was also bypassed this way. There used to be many different, so-called premium software or paid software, which used to be cracked in this simple manner. The very fact that the license key used to be a single license key, which was common across an entire version. So if the company had three versions, say personal, business, and then enterprise grade or custom, usually the personal and the business versions will have a hard coded key, and then the enterprise one would be like per user basis key provisions, because the country was trying to maybe cut costs down on license check systems, or whatever the reason may be, right? And this allowed hackers to just go ahead, run a simple command, and just get access just like that to that program. And this happened, I remember, in 2007. I remember checking many binaries, so-called commercial binaries, that had some kind of lock on them on Windows and on Linux, and finding that it was just stupendously easy to get the license key one way or the other. And it's even easier to patch the binary. Now, patching the binaries is not something we'll be discussing. It's an advanced topic here in this course, but I feel like at least you should know, so that something like this exists. So again, that's not really here nor there, but what I'm trying to make a point of here is that it is very easy to extract data stored in the .data section. So you might not want to store, important data in this section. Okay. Now the .bss section is an interesting section to say the least. Okay, when you're reading data from disk file, for example, you need to have a place for data to go after it comes from disk. Now when I say disk file, it can be a hard disk or a ssd as well, just so you know. Data buffers like that are defined in the .bss section of your program. You set aside some number of bytes for a buffer to give the buffer a name. You don't say what your values are to be present in the buffer. There's an important difference between data types defined in .data section and data items defined in the BSS section. Data items in the BSS section add to the size of your executable. Data items in the BSS section do not. I would like to point this out. This is extremely important point. Please note this down. If you've been taking notes throughout the course, this is one of those things you want to circle on your notebook. Dot data actually increases the size of your executable. .bss does not. That does not mean that .bss during runtime may not inflate. Again, listen to what I'm saying. Okay, and if you ever do a reverse engineering course with me and with Cybervidyapeeth, then you'll come to know more about these kinds of things, of how binaries can actually shoot up in size during runtime and may even fill up your RAM completely. An example of this might be a video game, right? For example's sake, I'm going to take a very heavy game, something like Rockstar Games, Red Dead Redemption 2. It's a graphically intensive game, very very it's a marvel of game engineering. And if you ever try to run it on any kind of system with every setting maxed out, every graphical fidelity setting, you will realize that even a 24 gigabyte RAM configuration in your system, or maybe 32 gigabyte RAM configuration, you will fill more than 21, 22 gigabytes of your RAM. Just let that sink in. Just how much data a single game can write to your RAM. And it writes more than 20 gigabytes onto your disk when it's actually running. It's all temporary data, but it's data nonetheless, which is generated on runtime based on your system configuration, how you like to play the game, where you are in the game, how the textures need to be based on the graphical settings you've selected. So there's a lot of stuff right there. Okay. And what's important to note here is that if a simple game can have this much data being generated, then what about complex machine learning algorithms and data science programs? That kind of workload, you will realize that normal systems really can't handle that much load. Again, not getting too deep, this is not an advanced course, but yeah, just trying to give you a whole horizon of what's going on. The next section is called the .text section. Now the .text section contains the program's actual machine instructions. Okay. In .text, no data items are typically defined. Please note typically right there. It's not to say that you cannot define it. It's just typically the case. Beyond your instruction mnemonics, the .text section only contains symbol called labels that specify locations in program code for jumps and calls. The Linux linker and the Linux loader, or the BSD linker and loader, cannot see any global labels outside of your program unless they are declared in the .text section. So if you want to understand in simple terms, most of the assembly language code you will write will be in the .text section. And when you're reverse engineering your own written binaries using maybe Redare, IDA, Binary Ninja, x64DBG, Ghidra, any tool, you are probably looking at the code extracted from the .text section. That's what you need to understand right now. Now, let's talk a little bit about a variable in assembly. So variable is defined by associating an identifier with a data definition directive. Data definition directives look something along this. So here's a simple data definition directive. We have my byte, a label, or an identifier as it's called sometimes as well. Then we say that it's a DB value or a data definition value. And it stores 07H, which is basically 7 in hexadecimal, which requires 8 bits to store. Then you are storing 16 bits, in my word, and it's not a data byte, it's a data word. So you see that, you see this right here, how db became dw, and then if it's a double word, then it becomes dd. Keep that in mind. Okay, we will be coming back to this soon. So I want you to just have a look at this code right now, how simple it is to declare a variable. So let's talk a little bit about string variables. Right? String variables are interesting special case. So you notice that, here when we are dealing with numerical values, we have to mention if it's a word, or if it's a double word, or if it's a quad word, or it's a byte, it's a nibble, whatever the case may be. But if you come here, you realize that string variables are a special case. A string is just that is string. It's a sequence or string of characters. This is extremely important. All in a row in memory. This is also very important, that if a string is stored in memory, it is going to be stored all in the same place. Listen to me very carefully. I did not say that the password you have written for your binary needs to be in the single place. I said that if that password is stored inside a single string label or identifier, then it's probably in memory in the same place, one after another in a row. For example, if your password is password and it's stored in memory, one thing you can do is that you can have a separate label for P, a separate label for A, a separate labels for SS, like so. And then you can expect them to be in different places. So you always have to account for these kinds of things. One string variable is defined in the eat syscall.asm, and I'll show you eat syscall.asm in just a bit. It's a very simple syscall file. It's not really complicated, but I'm not showing it because that's going to be the most complex we go in this course. We are not going more complex than system call manipulation. So here you see a simple label eat message, which is a db value, and it just says eat at Joe's, comma 10. Now can somebody tell me why comma 10 right here? Why we have comma 10? Exactly. I can see some people writing in the group. Yes, exactly. So if you ever see the number after a label in assembly, it's probably because it's the length of the string. And let's count, right? Eat E1, A2, T3, space 4, A5, E6, space 7, J8, 9, 10, 11, 12, 13. That's weird, isn't it? I just said that this is going to be the length of the string, but why is there 10? So what does the 10 signify there? Who can explain this to me? No one? Cool. If that is the case, I'm not even going to answer that. Let's see how many of you can Google up the answer yourself. What is that number when you define a label in assembly? That's all you need to search on Google, okay? This is again a very simple concept which is called equals to. This is a simple trick in assembly that is used to quickly calculate the length. So it should actually show you the length. Yeah, there you go. Eat len equals to eq, equ minus dollar minus eat message. Dollar usually here represents your label point or entry point. So this is an example of a larger class of things called assembly time calculations. Assembly time calculations, again, not going too deep into them. Here we are calculating the length of the string eat message. The string is basically just a label, remember that, and making the length value accessible through the label eat length. At any point in your program, if you need to use the length of eat message, you can use the label eat length. The statement containing character equ is a equate, yeah, or equals to as it's called. An equate is a way of associating a value with a label, such as a label is treated very much like a named constant in languages such as Pascal or COBOL. Anytime the assembler encounters an equate during an assembly, it will swap in equate's value for its. Now, before we get too ahead of ourselves and start learning other things other than variables, I want to take you back to the stack. Here's some basic information about the stack. Now again, not wasting too much time, because I've shown you multiple diagrams of stack and I've shown you how stack moves up and down. So this information again is for your your enrichment of your knowledge. So please just have a look, and you can ask me any question regarding this. So just go ahead and ask me any questions if there's any doubts. No question? Perfect. So let's move on. Again, nothing too much to explain. The figure is pretty much self-explanatory. You can pause the video right here and just go through the diagram once. We have discussed all of this beforehand. So this diagram of a stack is reversed, meaning I'm showing it to you bottom up, top down. I'm sorry, top up, bottom down, not bottom up, top down. Bottom up, top down is what I've shown you. Here's a stack in program memory. Again, all of this has been explained, so I don't want to spend too much time here. I've gone into all this before, so just for your reference, here's another new diagram for you. Have a look, and we'll move on. Okay, so push instructions are very special. You have push F, push FD, push A, and push AD as well. You can see what each of those do right here on your screen right now. Not going too deep into the other variations. As I said, this is not an advanced course, so I don't want to waste your time talking about many of these obscure instructions, which is true. Actually, you will rarely see these being implemented when you're doing manual assembly coding, but okay, fine, they exist, you need to learn about. Here's an example of what they do and what they push into. Just have a look. You might want to pause your screen. Yes, one for pop and all its variations in x86. Have a look. Please remember, all these instructions have been taken from the Intel Assembly Language Manual 2012 and 2017. For those wondering, you can download both of these manuals for free from Intel's official website. Here's another example of push and pop. I've again gotten much deeper into what push or pop does, so there shouldn't be much worries. If you want to do storage for short term, what do? So the stack should be considered a place to stash things for only short term. Items stored on the stack have no names and in general must be taken off the stacks in reverse order in which they were put on. Remember how we were pushing and popping in kind of a symmetrical manner when I showed you the program last time around? Keep that in mind and read this sentence again. You'll trust to see why that was the case. Last in, first out. Remember, LIFO. That is what literally LIFO means. For a lot of people who've been through college and still don't understand LIFO and FIFO, there you go. One of the best use of stack allows you to have all too few registers to do multiple duty. If you need a register to temporarily hold some value to be operated on by the CPU, and all the registers are in use, push one of the busy registers onto the stack, do your thing into the register, and then take the data back from the stack into the register. This is something very common, and we'll be doing this a lot. I recommend that when you are learning assembly programming, right, and you're coding in assembly, you prefer always, and mark my words, you always prefer trying to not touch the memory. The more, the lesser you will touch the memory, the more optimized your program will be. And it is a very, very hard job. Okay, it's very hard because there's a limited number of registers, and I honestly think, with today's decreasing hardware prices, processor manufacturers can actually etch in maybe 10 or 15 more registers. Yes, it will add maybe a few additional R, 17, 18, 19, 20, 21, 22, 24, 25. But at least, these additional registers will be able to hold 64-bit values, and they will make, assembly programming so much easier, at least for complex programs. Now, the int80 call on Linux is a fantastic call. It's a system call, as we call it. And, it lets you run things through the operating system. So to understand the operating system, an operating system is like a god and something like a troll. And Linux is no different. It controls all the most important elements of the machine in a godlike fashion. The disk drives, the printer, the keyboard, the various ports, Ethernet, USB, Bluetooth, and so forth, as well as the display. Okay. Please note, at the heart of the program is to call the Linux operating system, performed by the int instruction with the parameter ATH. So if you do int ATH call, you are calling the operating system to do some job for you, right? An operating system is still the god here. It's still the thing that runs everything, just so you know. This is an interesting topic. So before we get too much into this, I want to talk about interrupts and what interrupts are. Back in the day, when you wanted to do something that was not clearly defined, and when I say clearly defined, I mean to say that it was not considered, something, like that can be done by the computer in a single clock cycle. What used to happen was, say that the computer is doing something, right? Okay. And it can only do 3 simple calculations at once. It can do addition, it can do subtraction, it can do one more addition. That's it. A very basic computer. Okay. Now, if I tell you, okay, do one thing, take this, addition, subtraction, and addition again, and do a subtraction again somehow. And you can actually, prefer this subtraction over the first addition. So the first addition can be stopped while it's happening. And say the computer is slow, say it takes 2 hours to do the addition. Back in the day, that was the case. So now what would you do? So here we introduce something called as an interrupt. Say that, you introduce an operating system interrupt. So the operating system, for just a few nanoseconds or clock cycles, as it's called, stops and switches its attention to something else. In its core, that is what an interrupt is. Now, the interrupt can be hardware based as well as software based. There are hardware designed interrupts as well. For example, the power off interrupt. When you switch off your computer by pressing the power button for 10 seconds, also known as the 10-second switch off, or if you keep pressing it for 20-25 seconds and it reboots, these are both hardware programmed interrupts. No matter which operating system you use on your system, may it be Solaris, BSD, Mac, Hackintosh, Windows, doesn't matter. Some operating system you made, when you press the power button for 10 seconds, your system will shut down, no matter if you have coded the logic or not. So this is hardware interrupt. Okay. Then there is stuff like software interrupt. Okay. Things like, okay, I'm opening a dialog box. I want all the background to start getting a little blurry and faded. Okay. I want GUI elements to look, a little more blurry, and I want this window to be specifically focused. Something that elementary OS and Mac OS does a lot. So these kinds of things are actually where interrupt comes in handle in modern world, but in assembly language, we need to understand interrupt from a different perspective. So at the start of x86 memory, down at segment 0, offset 0, is a special lookup table with 256 entries. Okay, simple to understand. In the very start of your RAM chip at segment 0, offset 0. So first, segment and first, literally first place, first line, there is a lookup table with 256 entries, which goes from 0 to 255. Okay. Each entry is a complete memory address, including segment and offset portions, for a total of 4 bytes per entry. Clear? Shouldn't be too complex till here. You following me? The first 1024 bytes in memory in any x86 machine are reserved for this table, and no other code or data may be placed there. Again, very simple logic, nothing too complex. Each of the address in the table is called an interrupt vector. I hope you're taking all this down, okay? The table as a whole is called the interrupt vector table, the IVT. Each vector has a number from 0 to 255, as I was talking. The vector occupying bytes 0 to 3 in the table is vector 0. Yes, that is true, correct? See, 4 bytes, 0 to 3, 4 bytes, it's called vector 0 because it's at segment 0 of offset 0. Okay, offset is just the address, okay, in relation to the memory. So the vector occupying byte 4 through 7 is vector 1, and so on. Yeah, so that should be pretty easy to understand. So this concept shouldn't be too complex. I'm coming to interrupts in assembly in just a second. First, I want to make sure that everyone understands what an interrupt vector table is. So if you don't understand, I'm gonna give you guys about a minute or so. Okay, you can ask a question. By the way, until then, I'll actually answer other questions. So someone has asked that 10 represents EOL, end of line. Good job, good job, good job. Can you elaborate it more? Yes. So you want to think of it like this, okay? This is if you open the Intel manual again, and I'll show you next class, I'll show you the entire Intel manual. I'll skim through it. So if you open the Intel manual, this is just one of those things. When you're dealing with strings, you have to pass a string terminator or a line terminator. EOL works like a line terminator in assembly. Okay. When you're dealing with Python, this is added automatically to your strings. For example, if you say print hello world in Python, then automatically the string terminator is added. When you're dealing with something like, say, printf, then you can actually manipulate printf and scanf. If you remember, yes, last class, then we were discussing how these functions are vulnerable to injection of line terminators of different kinds in programming languages, and they can actually cause a lot of issues. The other question is, can we override hardware interrupts? Technically, yes. Practically, it is very hard to do. Why do I say technically yes? So there is an entire genre of attacks called the power analysis attack. What you can do is you can control the flow of power to the CPU and its pins, and by doing that you can actually control the execution of the CPU. You can become the god of the CPU instead of this, CPU becoming the god. So let me ask you this. CPU is executing some code for a program, and the program has some license check validation system. Okay, before the function which checks the validation is hit, if you cut power for a very minuscule time frame, and then you plug the power again, what do you think will happen? The CPU loses power, right? Just for a very minuscule second. The values are not erased from the RAM. The registers probably still have enough voltage to hold the value, and then power comes back again, and it's as if the CPU never died really. But during that time, CPU's execution clock cycle was skipped. So the instruction that the instruction pointer was pointing on can be manipulated or even jumped. Now, I'm not going too much into hardware hacking and power analysis, but this is actually how Apple AirTags as well as Starlink satellite dishes were hacked. And basically, any piece of hardware can be hacked like this. And this is just a simple vulnerability that is inescapable. At least from the research I have done, I've not seen any piece of hardware in the world which can, stand up to power analysis attack. As long as you are good enough at it, you will manage to break it. And once you are in, you then it's all a software, and software is buggy always. So you can always, fuzz your way through with a bug. So that is something to keep in mind. Okay, power analysis attacks are definitely something real, and we can override hardware interrupts and manipulate them, even change them even if need be. But again, practically very hard to learn skill, very hard to do, very few people in the world can achieve. For now, EOL is 10. It's manual defined, intent manual defined. So here's the interrupt vector table in front of you. Here you can see that vector 0, vector 1, vector 2, 4 bytes at a time. The lowest location is x86 memory. Here you can see 0000H. Then you have 000004H, 8H, CH, and 10H. 4 bytes at a time. Remember that. Okay. This is your simple vector table, the interrupt vector table. Okay. Shouldn't be too confusing to understand. Also, please note something about addresses, that the actual physical addresses that are etched onto your RAM stick are only accessible by your CPU. I repeat, the physical memory addresses etched into your RAM stick that you put into your computer are only accessible by your CPU. The CPU never exposes it to the operating system in the first place, and because it's not exposed to the operating system, there is sort of a virtual versus logical address mapping going on. And we'll come into address mappings also a little later. Memory addressing is again too complex to cover in this simple course. 5-day course is not long enough. Memory addressing will take me week to really jolt down. But if I had to put my finger on it properly, I would tell you that the addresses you see in your IDA Pro or Binary Ninja are not the physical addresses that are on your RAM chip. Just keep that in mind. Now here's a simple example of writing an interrupt vector into Linux. When a vector 80H, right, is called, and what happens is that the address at vector 80H takes execution into Linux system called dispatcher. This is a component inside the Linux kernel. Okay, this also exists in BSD, Mac OS, and Windows. Okay, though the call value may be different. So here in Linux and BSD, it's considered 80H. If I remember correctly, I think it's same for BSD as well. So it goes to dispatcher, right? And you can also see that the int 80 instruction call first pushes. So go to the top first of all, actually. Just give me 1 second. Yeah. So start at the top. We see that int 80 instruction, adds the vector and contacts the dispatcher. Then the next instruction, is pushed onto the stack, and the execution continues. The dotted lines you see here, right here, divide the user space and kernel space. If you have to understand this right now, in one sentence, I will tell you, user space is your system calls, your APIs and libraries, and your PHP and your Java and all that stuff. And most of the applications and graphics you see is user space, and even the applications you write. Kernel space code is a little different. It's kind of the thing that bridges the gap between application software and hardware. Okay. Here's a diagram of how we return back execution from a interrupt. Okay. You can pause your screen to look at this. This is extremely simple, not going into this right now. The arrows are pretty self-explanatory. Again, remember that the dotted line shows, above the dotted line, we see user space, things the user can control. And below that, we see kernel space, which require admin rights on the Linux kernel and cannot be controlled in Mac OS and Windows. Okay. So Linux BSD, you can control the kernel space if you wish to do so. But in Mac and Windows, you cannot do that because they are proprietary software. So again, here's some information about software interrupts versus hardware interrupts. The last line I'll just read because it looks like it's been cut off just a little bit. So with a hardware interrupt, the triggering event is an electrical signal applied to the CPU chip itself without any int call or instruction taking head in the process. Okay. You can read the rest of the text in front of you right now by pausing the video and going forward. If there's any questions, feel free to ask in the chat right now. Okay, so there doesn't seem to be any question. Let's move on. So we'll talk with a basic single parameter passing. Here is a function. Int func, int a, passing an integer as a parameter. Int I equals a, return I. Okay, so we're just passing a back to the user. Here we are returning func 11 in hexadecimal. That's 11h, okay? 11 in hexadecimal. So it's an integer. You need 8 bytes. Let's come this side. Move double word pointer address of the stack pointer plus 8 ECX. Inside the func, you will see this code. Now, if you come to the main, here you will see that we are subtracting the stack pointer by 28h. Then we are putting the value 11h or 11 hexadecimal into ECX. Then we are calling the function. Then the function execution happens. And the value of ECX is stored somewhere in memory. Then RSP is subtracted by 18. I'm sorry about that. RSP is subtracted by 18. So remember that RSP was subtracted by 28h before, right? And now it's subtracted by 18. So in total, how much was it subtracted by? Come on, this is basic math. Fast, guys. If RSP was subtracted by 28 before, how much it becomes when it is subtracted by 18 again? Exactly. So it becomes 10, right? Now, inside 10, so imagine the value becoming 10 for now if it started from 0. We see EAX, a value from dword pointer being shoved into the EAX register, and this is happening all because of this logic, okay? Int I equals a, return I. So we need to now create a label I in memory, allocate the value of a into I. So you will see that, you know, the value goes into a temporary storage, registers used, and there is some shuffling going on. So to be very honest with you, these 3 move instructions is just the shuffling you see right here in this signal. Finally, we add the RSP by 18 again, getting back to minus 28h if we started from 0. We ret or return with the value of RSP, and this logic actually just points RSP to the value of I, okay, or A, because I, A are same. And then when you return by default takes the value of EAX unless mentioned otherwise. So EAX value is taken up, and then we add RSP to 28 by, you know, pushing the stack pointer up, and then we return. Okay, so we return to main, and from that point onwards, the operating system handles the return back. So this is a very, very simple example right here in assembly. If it was, you know, not properly understood, you can ask me to explain it again. Okay, perfect. I'll move on. So give me 1 second. There you go. So here is a very, very simple example of how it will look like inside the stack if we zoomed in at a very high level. This is still not the lowest level of zoom possible. Okay. I want you to read this, understand this, start from the left side. Okay. Don't let it overwhelm you. And all the values are here hexadecimal, or register addresses are also hexadecimal. Okay, everything is hexadecimal here. And ECX, RCX, RSP, ESP, all these are registers. Okay, look at the document. I just want this document, to not look too daunting and to just sink in. So I think that much time is enough. Let's move on. This is very easy. Same thing I installed and explained right now with a small nitbit that I don't want to explain right now. I want you guys to figure it out. This diagram has everything you need to know. Everything. Okay. So what happens when you pass more than one parameter? It looks this horrible. So this is the code for func and main. Again, you can pause here to read further. But basically in x86 32-bit, most of these arguments are passed into the stack, onto the stack. Okay. If it's 64-bit, some are passed into registers and then onto the stack. Okay. Which registers are used for the list? Please refer to the Intel Manual 2017. Here's another diagram for the previous lines of code. You can pause here again. Here's something super interesting about Microsoft Windows mentioned. Not spending too much time here right now though. Okay, so let's talk about the ABI calling convention a little bit. So the default calling convention for the x64 application binary interface, or ABI, is a 4-register fast call. For callees, so people who are being called, to save those registers, space is allotted on the call stack as a shadow store. And this is actually mentioned here. If you go back, we have a small pop-up that says, hey, a pattern emerges, say hello to Microsoft's shadow store. So even if the callee doesn't take that many parameters, so let's say that we don't have more than 5 or 7 parameters, the callee must still reserve enough space to hold at least 4 register parameters. This is very important. You should be able to hold on a 64-bit system at least 4 parameters inside registers. Okay. Any additional parameters must be saved onto the stack after the shadow store, but before the call according to the specification. The stack will always be maintained in a 16-byte alignment except within the prologue. We'll talk about the prologue in just a bit. The Microsoft compiler, MSVC, specially uses a calling convention that not only stores the first 4 arguments in shadow memory onto the stack, but also passes them through registers. This is very weird. I know I've seen this especially in IDA quite a few times. I do not like this calling convention. I think BSD Linux do this better. If necessary, the callee is in charge of dumping the register parameters into their shadow space. Even if no function parameters are provided to another function, the compiler retains this space. Please note that. There is empty space retained by the compiler. Though you are not the compiler and you might be able to escape the convention. Remember, the words here are conventions, conventions, conventions. This is how people recommend you code, so that it's easier for you later. But if you are someone who's just trying to break everything and still make it work, break the rules and make it work, you might, give up on the convention. Here's a simple example of the subroutine again, and I'm not going to waste too much time here because I've shown this code again. So what I'm going to do is just show you this diagram that I've made. You can just go ahead and have a look at the diagram. Let's move on. Let's talk a little bit more about calling conventions. So register conventions, caller save registers. So caller save registers are also referred to by Microsoft as volatile registers. In other words, the caller must expect that the callee will update any registers that belong to them. Therefore, it is caller's responsibility to save the value before calling a subroutine to restore the value when the function returns. So if your function is the caller, it needs to make the necessary changes beforehand. In Visual Studio, this is how it works. You have RAX, RCX, RDX, then you have R8, R9, R10, and R11. If you're using GCC on Linux, then you have R8, R9, R10, R11, REX, RDI, RXI, RDX, and RCX in the following order that they are mentioned. If it's a Collie save register, additionally known by Microsoft as non-volatile registers, in other words, the caller should presume that the Collie won't change. Registers the caller as belonging. The caller must ensure that values are saved and restored if it needs to use more registers than the caller has, so as to avoid causing caller any problems. Here are Collie save registers on your screen right now for GCC and for Visual Studio. There are some conventions for register balance. The first point to note here is that both caller and callee are responsible for balancing any register saves they perform by adding them to the stack with restores or reversals, meaning removing them from stack. Caller will typically save registers right before the call and restore right after the call. Callee will typically save registers at the beginning of the function and restore at the end of the function time. A portion of caller save registers are used in x86 64-bit compilers to pass parameters in and out of routines. For example, RAX versus RDX, the return value is transmitted by RAX. Anything 64 bits or smaller is held by RAX. It is possible to return 128-bit values using RDX and RAX. So we divide the 128-bit value into two 64-bit values. 164-bit goes into RDX, 164-bit goes into RAX, and then we can return 128-bit values on a 64-bit machine approx. Parameter conventions. Microsoft x64 ABI. The first four parameters are placed into RCX, RDX, R8, R9 correspondingly from left to right. Other parameters are pushed onto the stack so that the parameter on the left is at the lowest address. Though typically move is utilized instead of push. This is interesting. Conventions for parameters for system V x64, x86 64 ABI, GCC as well as LLVM to some extent on Linux. The first six parameters are entered into corresponding fields marked as RDI, RSI, RDX, RCX, R8, R9. Other parameters are pushed onto the stack so that the parameter on the left is on the lowest address. Typically, move is utilized instead of push here as well. Please note that this is a more important slide for you readers because you'll probably be experimenting with Linux assembly first before you jump into Windows assembly. So please take a note of this slide. 32-bit stack calling conventions. So there are some calling conventions used in 32-bit programming. There is the CDEL, most common for C code, caller clears the stack, and then the standard call for Win32 API for Windows. The stack is cleaned by the call. The first function argument is placed at the lowest address when function passes parameters are pushed into the stack from right to left. Explicit stack frame linkage is performed by CDEXL and standard call conventions. The former ESP top of the stack pointer, which now points to the copy of EBP, which was the stack frame base pointer according to Intel convention, was relocated into EBP each time you enter a new function. If this statement does not make sense, use pen paper, create a simple to function and trace the function with the diagram and then come back to this line. It will make sense. It is common to refer to function parameters as EBP plus offset. Local variables frequently appear as EBP minus offset references, even though GCC occasionally refers to as ESP plus offset. So when you are trying to travel the stack, especially in the Linux world, I recommend using EBP plus offset or ESP plus minus offset. Okay, and you can go plus minus both with both of these. Okay, but for one of these there will be an issue. I am not going to show which one. Now here's a simple program. Okay, 64-bit to 32-bit. Just have a look. I want you all to pause the screen here and identify the changes. Here's a 32-bit stack frame for the 32-bit code. Here's the return address to main. So ESP points to the return address. Here's the stack top and stack bottom. Here's the saved EBP. Here's the return address for func to main. Then the saved EBP shows up. Let's look at a simple stack example again for this code. Again, this is very simple C code right here. First of all, a return address to the main is put by the invoke main function at the bottom of the stack. ESP points to this right now. Then the main frame is created. Then the saved EBP value is pushed onto the main frame. Then the int C happens. Then the function argument x equals to 7 is passed. Then the return address foo to main is also put on the main frame. Then the saved DBP and int b in the foo frame. Then the function argument y equals b is executed. Then the return address bar to foo is executed. And while this happens, a frame for bar is also created. After that, the saved EBP shows up inside the bar frame. Then the int a shows up. Then the EBP value is updated. And that's it. The program is. So I think this is a very nice animation to show you how it happens in the stack. Please go back and have a look at the entire animation and how I'm explaining it again. If it's a little confusing, please keep going back and listen again and again and again and again. You'll understand it's not rocket science. Also, please make sure here that you are understanding this part, because if you understand how things go on a stack and how they are called one after the other, then you are already halfway there. RMX addressing reminder. So please note how we use RMX addressing forms by Xenon. Now we have the Lee instruction. So we have talked about move, push, pull, nop, push, pop, nop. Let's talk about Lee for a second, which is load effective address. It is frequently used with pointer math, though occasionally just for math in general. An example of this is if RBX is equal to 2 hexadecimal and RDX is equal to 1000 hexadecimal, then LEA RAX, RDX plus RBX into 8 plus 5, the address that is at this point needs to be put, gone to. So you need to go to that address, take the value of that address and put it into RAX. Okay. So RAX becomes 1015, not the value at 1015. Okay. When the compiler encounters special math that can be calculated in the form of a plus b into x plus y, which is a lot of different math. Actually, this is a very flexible way of doing mathematics. It can compute the result more quickly if it utilizes the Lee instruction rather than, for example, the I instruction. Okay. There are two forms of flow control that we need to talk about. So we are now discussing, just a little bit about flow control or control flow. Conditional and conditional. You can think of flow control or control flow as for, while, all that stuff, for loops and while and if else in C language, something along those lines in assembly. Here we have two forms. Conditional, so go somewhere if a condition is met, things, if, switches and loops. Unconditional, always go somewhere, function calls, go to, exceptions and interrupts. Okay. The first one that we'll talk about is the jump. The simple jump, not any of its other variations right now. Though usually when you're reverse engineering, you'll see variations only. For now, I just want to talk about jump. Jump can be identified as unconditionally change RIP to a given address. So unconditionally, so it doesn't matter the condition, it will change RIP to a given address. Frequently used in small loops. So yeah, that is true. Some disassemblers will indicate this with a mnemonic by writing it jump short. Jump -2 is an infinite loop for short relative jump. Yeah, you guys are gonna have fun with that, aren't you? Jump doesn't have the number jump anywhere in it. It's really just jump OXC bytes forward. So I want some of you to actually tell me what that means. Let's see if you can do some basic conversion, right? Near relative RIP equals RIP instructions of next 4 bytes plus sign extended to 64 bits displacements are also shown using jump. Near absolute indirect address is also calculated by RM 64 bit for. So what I want you all to do is read through this slide again at least twice before we go ahead. If there's any questions, feel free to ask in chat. Yeah, so there doesn't seem to be any questions, so I'll move ahead. The leap is executed if the condition is true. If not, it moves to the next instruction. Jump if not equal, jump if not zero, both check if the zero EF flag or CPU flag is equal to zero. Here are some basic mnemonics for you. You can please have a look at each mnemonic here. Not going through every variation of jump. Jump is very interesting. It is basically how you jump up and down in assembly code. So you can pause your screen right now and just have a look at this. Now let's talk a little bit about comparing and compare. So the second operand is subtracted from the first operand to accomplish the comparison, and the status flags are then set similarly to the sub instruction. What makes doing the compare different from subtraction is that the difference of the sub, the outcome must be stored. Compare computes the result, sets the flags, and discards the result. That is the difference between a subtract and a compare. It modifies this carry flag, the overflow flag, the SF flag, the ZF flag, the AF flag, and the PF flags. Okay. Again, you can go back to my previous classes to see the names of these flags. I am hoping that you guys are taking notes because there's going to be a lot more information in assembly, as I've told in the first day only. So you'll have to make notes. The terms for unsigned and signed documents differ, resulting in various assembly instructions for signed versus unsigned comparisons, which suggests that based on whether a variable was defined as a signed or unsigned variable by the programmer, the compiler generates different code. This can be used to determine if variables are most likely unsigned or signed by a reverse engineer or a decompiler. Then let's look at a switch statement, a simple switch statement in memory. Again, I want you to write this code. I want you to compile it. I want you to decompile it yourself in GDB or Redare or IDA or Binary Ninja or Ghidra. Does not matter. The tool is just that, a tool. Okay, decompile it. Have a look at it. I am not going to explain this. See, because every single line, if I start explaining, now this course will take us years. Assembly is that complex and that big. Here, there is something very simple happening. There's a pattern here. Let's see if you can figure out the pattern. There's a pattern here with moves, jump pairs, and jump and compare. So let's see if you can figure it out. Let's talk a little bit about Boolean instructions now. Here's a simple code that deals with unsigned long main, then you have unsigned int I, unsigned int j. You also have you unsigned integer 64-bit k. You have a complex, complex calculation being done, and here is the entire code that was generated for main. Okay. There's also the AND. Now the bitwise AND is slightly different because bitwise operators deal in bits. Okay, they don't deal in raw values. So if you pass hexadecimal also, the hexadecimal values are actually converted to binary and then did. The OR bitwise as well does pretty much the same thing. You can pause the screen to read. Then you have exclusive OR. Again, the exclusive OR logic, I'm not going to waste my time explaining this. If you wish to learn about the AND or not XOR logic, then you can quickly Google that up. It's a very simple logic, not to waste time. Remember that this is bitwise, so it always converts whatever value, give it to binary, and then does the operation. We have ones complement negation, also known as NOT operation here. Now here's the first example of a simple shift. Can anybody tell me what a shift is before I explain it? Okay, no issues. So the SHL instruction is actually abbreviation for shift left. That is the first thing you need to know. Okay? It shift the bytes that you give it in the register to the left side one by one by inserting the same number of zeros from right to the end. The leftmost byte that is shifted is always stored in the CF flag or the carry flag. Here's a simple example of how it's done. Please pause and read through the logic that I just explained. Here's shift logical right, which does exactly the opposite. This also uses the carry flag. If there's any questions, you can ask them now. So that is it for today. Thank you so much for joining me. We have discussed shifts. We have discussed the LEA instruction. We have discussed quite a lot today. And I understand, today was a little bit info dump. I have dumped a lot of information on you. I completely understand, with this kind of information being flooded, but it's okay. I believe in you, and I really, really feel that, you all can truly master and understand these concepts, and you can be the change that is required. Please go back and watch the video again, so that you can learn and teach yourself all these concepts again and again. Remember that these concepts take time. All the content you need to learn, I've already shown it to you. You just need to give it time for it to settle in. Okay. And remember to always do your own research. Another point to note here is that our admission is still going on for post-graduation diploma in cyber defense by Cybervidyapeeth Foundation and Bhava University Hazaribagh. Feel free to scan the below QR codes to join our Telegram, apply to our course, or connect with us. You can also mail us at mentor@cybervidyapeeth.in or visit our website at www.cybervidyapeeth.in. You can call us on 971-114-7900. Please ignore the date that the last admission date is 31st of October. That date has been extended, and currently the admissions are still open for postgraduate diploma in cyber defense, the world's first and the most advanced diploma degree in cyber defense engineering. We hope to see you there. Thank you so much for joining me today. I hope to see you there again tomorrow in the final day for CERT-In session on Zero to Hero assembly language, the language of Cyber Defender. This is Professor Xerox signing off. Dhanyavad. Jai Hind.